Heat is energy. It's all around us. From the sun that warms our planet to the stove that cooks our food, thermal energy is the driving force behind countless natural phenomena and human endeavors. As we strive for a sustainable future, understanding and harnessing the power of heat becomes more crucial than ever. This is where thermal energy processing comes in. Thermal energy processing encompasses a wide range of technologies and techniques used to transfer, store, and manipulate heat. It plays a vital role in various industries, including power generation, manufacturing, transportation, and even healthcare. By mastering the art of thermal energy processing, we can develop cleaner, more efficient, and sustainable solutions for a brighter future. Imagine a world powered by renewable energy sources, where factories operate with minimal waste and pollution. Picture cars running on clean-burning fuels or electric batteries charged using sustainable methods. These aspirations, while ambitious, are within reach. The key lies in unlocking the full potential of thermal energy processing. This journey begins with understanding the fundamental principles governing heat transfer and applying this knowledge to design innovative technologies. Join me as we delve into the fascinating world of thermal dynamics and explore how it can pave the way for a brighter, more sustainable future. To navigate the intricate world of thermal energy processing, we need the right tools. These tools are not just physical instruments, but also mathematical concepts that help us understand the underlying principles. Just like a mechanic uses wrenches and screwdrivers to fix and maintain machinery, engineers rely on mathematical concepts to understand and predict the behavior of heat and fluid flow in various systems. Three essential tools in this endeavor are the Reynolds, Prandtl, and Nusselt numbers. These dimensionless numbers are fundamental in the study of fluid dynamics and heat transfer. These dimensionless numbers provide valuable insights into the complex world of fluid dynamics and heat transfer, helping engineers to design more efficient systems. The Reynolds number tells us whether a fluid flow is laminar, smooth and orderly, or turbulent, chaotic, and unpredictable. This distinction is crucial for understanding how fluids behave under different conditions. Imagine a calm river flowing smoothly downstream. That's laminar flow. In this state, the fluid moves in parallel layers with minimal disruption between them. Now, picture a raging torrent crashing over rocks. That's turbulent flow. Here, the fluid experiences chaotic changes in pressure and flow velocity. The Reynolds number helps engineers predict this behavior, which is crucial for designing efficient pipes, pumps, and heat exchangers. Understanding whether the flow will be laminar or turbulent can significantly impact the design and efficiency of these systems. Next, we have the Prandtl number, which describes the relationship between a fluid's viscosity, resistance to flow, and its thermal diffusivity, how quickly it conducts heat. This number is essential for understanding the thermal properties of different fluids. Think of honey. It's very viscous and doesn't conduct heat well, resulting in a high Prandtl number. This means that honey resists flow and retains heat, making it a good example of a fluid with high viscosity and low thermal diffusivity. Water, on the other hand, has a lower Prandtl number because it flows more easily and conducts heat more effectively. This makes water an excellent medium for heat transfer in many applications. Finally, the Nusselt number quantifies the efficiency of convective heat transfer between a fluid and a solid surface. This number is crucial for designing systems where heat transfer efficiency is paramount. Convection is like a warm breeze carrying heat away from your skin. This natural process is harnessed in many engineering applications to improve heat transfer. The Nusselt number helps engineers determine how effectively a fluid can transfer heat to or from a surface, which is crucial for designing heat exchangers, radiators, and other thermal devices. By optimizing the Nusselt number, engineers can enhance the performance and efficiency of these systems. These three dimensionless heroes, Reynolds, Prandtl, and Nusselt, provide a powerful framework for understanding and predicting heat transfer phenomena. They are indispensable tools in the engineer's toolkit. By mastering these concepts, engineers can design more efficient and sustainable thermal systems, paving the way for a cleaner and more energy-efficient future. This knowledge is key to advancing technology and improving our quality of life. Heat exchangers are the unsung heroes of countless industrial processes, silently working behind the scenes to transfer thermal energy from one fluid to another. These devices are integral to the efficiency and functionality of many systems we rely on daily. From power plants to refrigerators, these ingenious devices play a vital role in our everyday lives. Imagine a car engine. Without a radiator, a type of heat exchanger, the engine would quickly overheat and seize up. This would lead to significant damage and costly repairs. The radiator uses a network of tubes and fins to transfer heat from the hot engine coolant to the cooler air flowing over it, preventing catastrophic engine failure. This process ensures the engine runs smoothly and efficiently. Heat exchangers come in various shapes and sizes, each optimized for specific applications. Whether it's a compact unit in a household appliance or a massive structure in an industrial plant, each design serves a unique purpose. The design and efficiency of a heat exchanger depend heavily on the principles we discussed earlier: Reynolds, Prandtl, and Nusselt numbers. These principles guide engineers in creating effective and efficient heat transfer solutions. By carefully considering these factors, engineers can design heat exchangers that maximize heat transfer while minimizing energy consumption. This balance is crucial for both performance and sustainability. For instance, increasing the surface area of contact between the fluids can enhance heat transfer. This is achieved through innovative designs and materials. This is why car radiators have numerous thin fins, to maximize their surface area and improve cooling efficiency. The more surface area available, the more effective the heat exchange process. Similarly, turbulent flow, characterized by a high Reynolds number, enhances heat transfer compared to laminar flow. Turbulent flow increases the interaction between the fluid layers, improving the overall heat exchange. The efficiency of heat exchangers is crucial for a sustainable future. Efficient heat exchangers reduce energy consumption and lower operational costs. By optimizing their design and operation, we can reduce energy waste in industrial processes, power generation, and even our homes. This optimization is key to achieving energy efficiency on a large scale. This translates to lower energy bills, reduced greenhouse gas emissions, and a cleaner, healthier planet. The impact of efficient heat exchangers extends beyond individual systems to benefit the global environment. Section 4. Evaporation, from simple boiling to complex industrial processes. Evaporation, the process of a liquid turning into vapor, is another fundamental aspect of thermal energy processing. This natural phenomenon is not only fascinating, but also incredibly important in both everyday life and industrial applications. We encounter evaporation every day, from the simple act of boiling water for tea, where the heat causes the water molecules to escape into the air as steam, to the drying of clothes on a sunny day, where the sun's energy helps water molecules in the fabric to evaporate into the atmosphere. However, evaporation plays a much larger role in various industrial processes. It is a critical component in many sectors, driving efficiency and innovation. It's essential for desalination plants that turn seawater into fresh water, providing vital resources in areas where fresh water is scarce. For cooling towers that dissipate waste heat from power plants, ensuring the plants run efficiently and safely, and for the production of various chemicals and pharmaceuticals, where precise control of evaporation rates can affect the quality and yield of the final products. Understanding the factors that influence evaporation rates is crucial for designing efficient and effective thermal systems. Engineers and scientists must consider multiple variables to optimize these processes. Factors like temperature, pressure, humidity, and the surface area of the liquid all play a role. Each of these elements can significantly impact the rate at which evaporation occurs. The previously mentioned dimensionless numbers also come into play, providing a mathematical framework to predict and control evaporation, as they can help predict the rate of heat and mass transfer during evaporation. This predictive capability is essential for scaling up processes from the lab to industrial levels. For example, a higher Reynolds number, indicating turbulent flow, can enhance evaporation rates by promoting mixing and increasing the surface area of contact between the liquid and the surrounding air. This is particularly useful in industrial settings where maximizing efficiency is key. Similarly, the Prandtl number can help determine the relative importance of heat and mass transfer during evaporation. Understanding these numbers allows for better control and optimization of the processes. By mastering the principles of evaporation, we can design more efficient desalination plants, which are crucial for providing clean water in many parts of the world, develop innovative cooling technologies for electronics and industrial processes, ensuring that devices and machinery operate within safe temperature ranges, and improve the sustainability of various manufacturing processes. By enhancing these systems, we can reduce energy consumption and minimize environmental impact, paving the way for a more sustainable future. Section 5. Predicting the flow of heat models and correlations. Understanding the fundamental principles of heat transfer is only half the battle. To design efficient and reliable thermal systems, engineers need to be able to predict how heat will behave in various scenarios. This is where mathematical models and correlations come in. These models and correlations are like equations that describe the relationship between different variables influencing heat transfer. For instance, there are equations that can predict the rate of heat transfer through a solid wall, the convective heat transfer coefficient between a fluid and a surface, and the rate of evaporation from a liquid surface. These models and correlations are derived from a combination of theoretical principles and experimental data. They allow engineers to estimate heat transfer rates and design thermal systems without having to perform countless expensive and time-consuming experiments. However, it's important to remember that these models and correlations have limitations. They are based on certain assumptions and simplifications, and their accuracy depends on how well these assumptions reflect real-world conditions. Despite these limitations, models and correlations are essential tools for engineers designing and optimizing thermal systems. As our understanding of heat transfer phenomena advances and computational power increases, these models and correlations will become even more sophisticated, enabling us to design even more efficient and sustainable technologies.